So it gives me great pleasure to welcome Dana Yang to give the ORIE Colloquium today. So I think many of us, due to the pandemic, did not realize who was being hired in other departments. And so it was a great surprise for many of us when quite a few of us knew of Dana's work. And then all of a sudden, one day we realized she was actually at Cornell. So she started off in statistics in this spring. So basically this semester. But before that, so she was at Yale, I guess, working with David Pollard. So must have been maybe his last student, or
technically not. There's another student who graduated after me.
So David's second last student,
Yeah.
working in sort of pure statistics, but then did some amazing, so did a postdoc with Jiaming Xu, who many of us know pretty well, and did some amazing work on thinking about like high dimensional sort of planted optimization problems and phase transitions of this. And then was a Simons fellow for a semester and is now here at Cornell. So we figured this is a good time for us and ORIE to introduce ourselves to Dana and have Dana meet us. And she is around in Ithaca, so hopefully you get excited with what she's going to talk about and catch up with her later. Over to you.
Thank you. Thank you so much for the such a nice introduction, and thank you for inviting me here. I'm just really happy to be here. Really, I came here like a few months ago at the start of the semester, and I've been loving it so far here. So I'm going to get started. I'm going to talk about the planted matching problem. So this is a joint work with my amazing collaborators and advisors, Jian Ding from Wharton, and Yihong Wu from Yale Stats, and Jiaming Xu from Duke Business School. So basically, I work on what you call planted models. And these planted models, you may be familiar with some of them, or you may even have worked on them. This is a really surging field, especially in the intersection of operations research and statistics and computer science. But basically, this type of models, they take a very simple form. So you assume that there is a random network, and this random network consists of some regular-ish planted structure and some random noise. Okay, so because there's a planted structure, there are a lot of fundamentally interesting problems you can ask with regard to when and how can you recover this planted structure. And usually when you ask the question of when, you can pose the question like a statistical inference question, because it's like how much data, how much signal do you need in order to reliably, statistically recover the planted structure. And you can also ask the question of how, which is more of an algorithmic question, meaning that can you recover the structure efficiently? Okay, so a lot of interesting questions that you can ask. And some representative examples of planted models include, for example, you have a planted click in an Erdős graph, and you want to recover this click. Or you may also be familiar with the stochastic block model. That's basically when the planted structure takes a block community form, and then recovering the planted structure is just recovering the node labels, which is just community detection. So the model that we're going to look at today is probably one of the simpler ones that I have encountered. So this is when the planted structure is a perfect matching in a bipartite graph. So all that means is you have n vertices on the left and you have n vertices on the right. And a perfect matching is basically a set of edges where each node on the left is incident to its unique match on the right, and vice versa. Okay. So under this model, we assume that the observed graph is some noisy version of that. And that noisy version is a graph that consists all the edges in the perfect matching. And also there are some random edges that just appear. So these are the edges that are sort of noise in the graph. And your goal is to recover what is the true planted perfect matching, or you want to tell apart which are the red edges and what are the blue edges. Yes.
Simple question. What is the meaning of planted?
Yes.
So why don't we say there exists a structure or there is a structure, but we say planted structure?
Yeah, so I think of it as a structure that is planted in the sense that you assume that it just exists to from day one, from the assumption of the model. So you can also think of like, say you have a bunch of edges and all the edges say they appear IID with some probability, then that's like an unplanted model where you have more like an Erdős Rényi graph, and you may ask questions of whether or not there is a perfect matching in the graph. But here I'm looking at the setting where there is a planted matching, so that is always going to be there. And I hope that answers your question.
And the shape structure of this, there's like four nodes, perfect matching on.
Yeah, that's the assumption.
So just kind of to follow up on that. So it is important that you are recovering the planted matching, because if the random edges were dense enough, there could be many perfect matchings.
Yes, exactly.
So you have to recover that specific one. Okay.
Yes, that's right. And sorry, yeah.
If there are many perfect matches, how would you know which one of them is a planted one or not?
That's a very good question. Yeah, so basically, that's what my work is about. My work is how many fake edges does there need to be for it to be no longer possible to recover?
But let's suppose you know everything. Let's suppose you spend infinite time. How would you know which one of them is planted or not?
Let's look at this example.
Sure.
Okay, I claim even though there are fake edges, you can still tell. So suppose we know that one is actually connected to 1', but suppose we don't observe the colors. And suppose I argue, okay, why can't 1 be actually connected to 3'? Well, that cannot happen because that means 1' must now connect to 2.
Sure. In this example, it might be the case, but there might be other examples in which there are multiple perfect matching, right?
You're completely right. Yeah. So our final result is going to take the form of when the average number of fake neighbors of each node is below a certain threshold, then it is with high probability you're guaranteed to recover.
Okay, so in this case, there will be just one perfect match, right? Okay.
Actually, I look at a slightly different variant of that problem. So that would be like the threshold for exact recovery. I'm going to look at the statement of whether you can recover almost all the edges. So you make basically a little one proportion of mistakes in the matching. Thank you. Thank you for all the questions. Let me first give some motivation for this mathematical model. Basically, so we're motivated by the particle tracking application. And this is how it works. So you have a bunch of particles that are moving around, and you're taking snapshots of their locations. So they move from one time frame to another, and your goal is to tell like which particle moved to which place between the different time points. And that is basically a problem of recovering an underlying true matching. Right? So these particles, it could be, for example, bacteria that are swimming around, or they can also be a flock of birds that are taking off. So by recovering the true correspondence between the particles, that means you can recover the moving trajectory of all the particles. And that is very crucial for the behavioral analysis of the organisms. So motivated by the particle tracking application, this is like a very abstracted model that we study. So under this model, we assume that there is a true perfect matching. And this true perfect matching is just distributed uniformly over the set of all perfect matchings, or equivalently uniformly over all permutations. And there are going to be some fake random edges. So for each edge that is not in the true matching, we assume it appears in the graph independently with probability d over n. Okay. And now we assume the edges, they come with weights on them. So the edges that are on the true matching, they follow some edge weight. Their edge weight follows some distribution p. And for all the other edges that show up, they have edge weight distribution that are equal to some other distribution q.
Is D here the degree? Oh, what is D?
Yeah, D is basically the degree. So, or the average degree. So because each fake edge appears with probability d over n, if you focus on one node, then the total number of like fake neighbors it has is on average it's equal to d. So it's like the average degree of the blue edge graph.
But the blue edge graph is a graph that is the random graph is a noise, right? So like that's not
the noise.
realized. Like how can you come up with D before realizing that the random graph? I'm not exactly.
Sorry, I don't fully understand.
So like
question.
Can I help? Can I do specify the use that to generate each edge?
I see. Oh, okay, D is a parameter.
Oh yeah, D is a parameter.
Okay.
Yeah. Okay. So that's how this is our model. And our result under this model can basically be summarized in one slide. So in short, we obtain the sharp threshold for almost perfect recovery. Okay, so let me be more specific what that means. So we claim that there is a sharp threshold such that when the signal strength is above this threshold, then there is some estimator that achieves so-called almost perfect recovery, meaning that on average, the total number of edges of this estimator that differ from the true matching converges to 0. Or yes, the proportion of edge converges to 0.
What's the definition of estimator?
Estimator is any function, potentially random function of the graph.
And the function has to take values in a perfect matching.
Oh, yes, that's right. Yep.
Okay.
Yep. Let me think. Do we need that? I think there's some kind of projection argument where you don't need the estimator to be a perfect matching. Like if your estimator is not a perfect matching, then you can always consider like the perfect matching that is closest to it. And I think its statistical performance by some triangle equality is going to be basically on par. So
I guess when you're writing some M achieves, is this just a information-theoretic recovery, or you know how to construct?
yes, so this is actually going to be the maximum likelihood estimator. So
Poly time, like, so there is no actual separation between the computational.
Yes.
statistical.
yes, that's a great point. So for this problem, there's no computational gap. Because here, finding the maximum likelihood estimator turns out to be just solving the linear assignment problem, which can be solved in polynomial type, for example, by the Hungarian algorithm.
Can
So,
you explain this notation a bit? Something, what the delta, what?
oh, sorry, yeah.
Yeah, what does that mean? Yeah.
Yeah, so let me explain. This is the symmetric difference between the estimator and the truth. So that's all the edges that are either in M hat but not in M star, plus all the edges that are in M star but not in M hat.
So that's a matrix or something, each of it?
That's the cardinality of the set.
Cardinality of the set.
Yeah, yeah. So
Okay.
this is like
Okay.
the total number of edges that got matched wrong. basically.
Okay, okay.
And because there are in total n edges, so divided by n, this is the proportion of mistakes.
And M star is unique already or what?
So M star is the truth that is assumed to be in the model. So
They are in the model.
So
Okay.
M star is the set of all the red edges. So M star is the true perfect matching.
This is assuming again, I was talking about the unique something that
Yes.
No,
that planted.
Yeah, under this model. there's
Planted
a
any
planted.
shape, anything, right? And M star is, doesn't have to be bipartite matching, right? Anything.
M star is assumed to be a bipartite perfect matching.
Oh,
So we model it in a Bayesian way that it's uniformly distributed in the set of all perfect matchings.
okay.
Yeah, but it's just up to symmetry. You can just imagine the perfect matching as is the identity matching shown here. By the way, so throughout this talk, I'm always going to represent the edges in the planted matching as the red thick edges, and all the fake edges are going to be blue thin edges. So our sharp, yes, please.
Do you know the bipartition then?
Sorry.
The bipartition of the graph? Like, is
Yes.
that's known?
Yes, you assume that's no. Yeah, but I think there is also a version of like just a univariate group. I don't think that knowledge is going to be very important. Actually, I'm not completely sure, but there's a version of this type of result for not bipartite graph, but unipartite graphs. And it's going to be roughly, the sharp threshold is going to sit at the same level. So even if the graph is not bipartite, you can still derive results like this. So I don't think like knowing one side from the other is going to matter too much. I'm not sure. Yes.
In your model, the fake edges are present with probability d over n,
Yes.
but the parameter d doesn't seem to appear in your theorem statement. So is there some hidden dependence?
Yes, here.
Oh,
Yeah.
yes, okay.
Yeah, I'm just going to get to that part. Yes. So, yes. So the sharp threshold is only going to depend on two things actually. One is d, which is the sparsity parameter. The other is the Bhattacharya coefficient. You may also know it as the Hellinger affinity between the two distributions T and Q. And it's only going to depend on these two quantities. So on one hand, we show that if through d times Bhattacharya coefficient is bounded by 1, then there is an estimator that succeeds. On the other hand, we show also the negative result saying that if this quantity is above 1 plus epsilon for however small constant epsilon, then no estimator can achieve almost perfect recovery, or that on average, they're all going to suffer a constant proportion of mismatched edges. So this is all our result. Yes.
Do you know if the theorem continues to hold for d tending to infinity with n?
Yes, great question. I was just going to get to that. We do. And in short, it holds, but we need some additional scaling assumptions. So first of all, I should point out that this sharp threshold was the first conjectured in the statistical physics community by Semerjian, Sikuro, and Zilberova. And what our contribution is, we're able to resolve this conjecture rigorously. And our result is quite general in that it holds in both the d-bounded sparse case and the d going to infinity dense case. So we do need some additional scaling assumptions when d goes to infinity. And those assumptions, to answer your question, they basically ensure that if you look at the, on average, d fake edges incident to each vertex, then by observing their weight, there's going to be basically a most likely one, the edge that is most likely to be the true one. And the scaling assumption is to make sure that that likelihood is on par with the red edge being the true one. So we have some kind of scaling assumption like that. Okay, so that's all of our result. And I'm going to give some examples of like.
Actually, just to understand this, if the weights were just one, if P and Q are just identity in one, what would this say?
Yes, you asked the greatest questions. I was also going to get to that. So when PMQ, let me just get to that now, actually. So this is basically when P and Q are just equal to 1. So P is equal to Q, the edge weights don't matter, they don't provide any information. In this case, the bipartite coefficient it just equals 1, and the sharp threshold collapses to E equals 1, right? So this is a really simple, nice result that says that if on average each vertex is attached to more than one fake edge, then you cannot tell.
So one more small thing. So if you flip P and Q, nothing changes, right, in your setup? They just need to be different, and you have to measure some sort of a
yes,
distance.
that's right. Yeah, yeah, because the bilateral affinity is symmetrical.
Can I ask another question? I'm sorry, we keep bugging you there.
Yeah, I love these questions.
So is the theorem sufficient to answer the question? So let's suppose you don't know if there is a planted matching or not. Can you test the hypothesis if there is one or not?
That's a great question. I don't know, actually. We haven't really studied the testing problem.
Okay.
Yeah, I don't know. I don't even know if our analysis is going to, it can be applied to that problem, but it's something worth pursuing. Yeah, here we go. But before I go there, I want to mention another special case. This is the case when D is equal to N. So you actually have a complete graph, all the edges appear, and the edge weights are assumed to be all exponential, but with different rates. So actually the unplanted version of this problem has a much richer history, and the planted version is studied more recently. And it was conjectured by some people before me, actually including one of the papers, including my advisor Jiaming Xu. So they conjectured that the sharp threshold sits at lambda equals 4. So we're able to resolve this conjecture as well, saying that lambda equals 4 indeed is the information theoretic limit. And but today I want to focus more on the unweighted model, because this result is like fascinating to me, because it's so simple. The threshold equals 1, and it just makes so much intuitive sense. And for a while, I just really thought that there should be a 3-page proof for this guy. But it turned out that when we actually got into the nitty-gritty details of analyzing this problem, like it's actually more involved than we thought. So what I want to do today is actually just focus on this unweighted case. So from now on, let's forget about auto weights. And let me try to convince you why D equals 1 should be the right sharp threshold. And I'm going to do that by highlighting some of the key arguments in our analysis, because really for this problem, in my opinion, like the analysis is even more interesting than the result itself. And I'm going to explain to you why, if you use some of the more standard methods in this field, they're going to automatically fail, and what we needed to do to overcome that difficulty. So let's just focus on the unweighted model now. We have a graph with a planted matching and a bunch of fake edges. And the fake edges, they appear independently with probability D over N. So we want to establish two directions, the positive and the negative direction, to establish the sharp threshold. And I'm going to start with the positive direction because it's actually the much easier one. So when D is smaller than 1, when the average degree is smaller than 1, I want to show there is an estimator. And in particular, the maximum likelihood estimator, I claim it succeeds.
So when D is equal to 1, what is the average degree of the graph? Is it 1 or is it 2?
Well, it's
so
actually
is this
2.
on top of the embedded matching? Okay.
So the yeah, you're right. The blue graph has average degree 1, and adding the planted edges, the average degree of the graph is 2.
Okay, and the N there is half the number of nodes, right? So nodes on one side.
Yes,
what we
that's
call
right.
it.
Yeah. I should have clarified that. Yeah. So, this is actually a pretty simple first moment analysis, but it's a good warm-up exercise. So let's look at what the MLE is. In the unweighted case, all the perfect matchings that show up in G, they have the same likelihood. They're equally likely to be the planted one. Therefore, the MLE in this case is simply just a member of the set of all perfect matchings that show up in the graph. Therefore, the event that the MLE differs from the truth by a certain number of edges is basically contained in the event of that there exists another matching that is also perfect matching, and all the edges in this matching also appear in G, and that this matching differs from the truth by this number of edges. Okay. And from here, it's basically just a union map. You count the total number of matchings that differ by from the truth by say T edges, and that by a simple combinatorial argument that can be bounded by n choose T times T factorial. And then for each of them, the probability that it actually shows up in the graph G is just equal to D over N to the power T, because you need the T fake edges to all appear, and they each appear independently with probability D over N. And therefore, when D is smaller than 1, you can show that this guy goes to 0, meaning that with high probability, you're going to make a very small error. Okay. So this is the entirety of the proof of the positive result. Yes.
So does this mean that you'll recover the hidden perfect matching then?
No, actually it
You'll
doesn't.
make very little mistake.
I'm sorry?
You will make very small mistake.
Yeah, so for any small constant beta multiple of n, you can show that with high probability, this error, the number of mistakes is bounded by beta n. Or I guess you can also put it in like the proportion of mistakes you make goes to 0 in probability. Right? And because it's a bounded random variable, you know that that's equivalent to saying that this proportion goes to 0 in mean. So.
But it's true for any beta, right? Not for it's true for any beta.
Yeah. This is true for any constant beta. Yep. And as a consequence of this, you can show that 1 over n of this guy, taking expected value goes to 0. So, the much more interesting direction, in my opinion, is the negative direction. Right. So we want to show that when D is larger than 1 plus epsilon, then no estimator can succeed. And that's usually the harder direction to show, because you need to sort of safeguard against all possible estimators. And as a result, now instead of analyzing the estimator with the highest likelihood, you're sort of forced to look at the entire landscape of the likelihood and analyze the posterior distribution as a whole. So let me be more clear what I mean. Our analysis relies crucially on 3 observations. The first observation is that no matter what estimator you consider, you are not going to be doing more optimally than the estimator that just samples from the posterior. And this is a very simple fact that took us way too long to realize, but it's a consequence of just the triangle inequality and the base rule. Okay. So what I mean is, if you take any estimator m hat, then the estimator that samples from the posterior m tilde, its error is going to be at most twice the error of impact. And that means if any estimator is to achieve almost perfect recovery, then so must the estimator that is sampling from the posterior. And therefore, in order to show this negative result, all we need to show is that the posterior sampling estimator fails. Is this clear? I realized that even though this is a very simple result, but we actually didn't, it's not something that came to our head at first when we first started analyzing this problem, and it's really useful to know. Now, the second observation that we use is, okay, we want to understand what the posterior distribution looks like. So in the unweighted case, it's actually very simple because we know the likelihood is the same for all perfect matchings in the graph. And the prior is uniform. Therefore, the posterior distribution is simply the uniform distribution over the set of all perfect matches. So our proof strategy goes like this. We divide the set of all perfect matchings into a good region, which is close to the truth, and a bad region, which is far away. And we show that there are many, actually an overwhelming number of bad solutions. And therefore, when you're sampling from the posterior, because note that the posterior is uniform, then there is an overwhelmingly high probability of you landing in the bad region, right? And therefore, you're going to suffer a large edge mistake. So that's our proof strategy. So in particular, we want to show that there are exponentially many alternative matchings that are far from M star in the sense that they differ by at least a constant multiple of n edges. The final observation is we want to look at, okay, what does an alternative solution look like? I claim that for a perfect matching M that is not M star, its symmetric difference with M star is going to consist of a disjoint union of alternating cycles. And here, alternating, I just mean a cycle that goes red, blue, so true edge, fake edge, true edge, fake edge, and so on. And this is just a simple fact resulting from the observation that each node in the that appears in the difference graph is incident to exactly one fake edge and one real edge. So now, with all these three observations, we have successfully reduced the problem of showing the negative direction into the problem of finding exponentially many long alternating cycles in the graph. And we want to find exponentially many of them, and we want each of them to be of length that is linear in n, because that means they must correspond to some alternative matching that differs from the truth by a constant multiple of n edges, and then we would be done. Okay. So far it's like the proof outline clear. Okay, so how do we do this? We want to find many alternating cycles. And an immediate idea that we had is just using the first and second moment method, which is one of the.
Sorry, I got a little lost. Why doesn't one long alternating cycle suffice?
That's because one long alternating cycle, they correspond to a bad solution. Okay? But that only means in the bad region, there is one member. But you could still have many solutions that are very close to M star. So if you sample from the posterior, you need to rule out the possibility of landing in the good region, which is why you need to show that the number of bad solutions are overwhelming compared to the number of good solutions.
This
naive bound on the number of good solutions, just in terms of the total number of matches.
Yes. Yes, that's right. Yeah. So I'm I'm basically ignoring some details here, but you can show that the number of good solutions in here is bounded by e to the constant multiple of delta n, and the lower bound is e to the some other constant of delta n, but it's a much larger constant. So there are exponentially more bad solutions than the good solutions. Okay. So usually for this type of statement, you want to resort to the first and second moment method, which basically works like this. So let S be the set of long alternating cycles. You want to show this set is large. So let's look at the first and second moment of the size of this set. The first moment is quite easy to deal with. We can work out to be indeed exponentially large. So that part is good. Now, if we can show that the second moment is on par with the first moment squared, then that means with at least some constant probability, the size of S itself is going to be also exponentially large. Okay? This is basically a consequence of Cauchy-Schwarz inequality. And the unfortunate case for us is that the second moment method is doomed to fail, because we can actually provably show that the second moment is much larger compared to the first moment squared. And that's because we're looking at these long cycles, right? So a lot of them are going to share a large number of edges. And when they share a lot of edges, they are highly correlated, meaning that if you know one appears in the graph, then it's much more likely that the other also appears. And this strong correlation eventually just blows up the second moment, right? So this second moment analysis it cannot work for us. And instead, our idea of like how we address this is quite simple. Instead of looking at long cycles, what we're going to do is first find or show the existence of many disjoint short paths. Then once we have these paths, we want to connect them into long cycles. So this is the sprinkling idea that has existed for quite some time. For example, it was it was used by Erdős in '98 to show like the emergence of joint components in supercritical order training graphs. And it was also used by Ding in 2015, but under a very different context. So it's known as a sprinkling idea because basically, yes.
Are these short paths alternating?
Oh, yes, they're also alternating.
And when they alternate, they have one real edge, one fake edge, one real. So they're not really disjoint, they're disjoint in the fake edges, I guess. Then.
Actually, we want them to be all disjoint. We want them to be vertex disjoint as well. And the reason is we want to connect them into long cycles. So we cannot have, like in alternative solutions, we cannot reuse vertices. Otherwise, they won't correspond to matchings. So the idea behind this sprinkling is basically you reserve a set of vertices and you don't touch them. Then you use the set of unreserved vertices to find a bunch of paths, right? And then in the next stage, you sprinkle on the reserved vertices and the edges that they come with. And these sprinkling edges, they help connect everything together into long cycles. So this is the idea. I should point out that this idea, it actually didn't work for us to start with, because what we want is that the short paths, they are very well connected to each other. So that, because recall that in the second stage, we're not just looking for one long cycle, we want exponentially long cycles. So we want them to really try to reach out and connect to each other. However, just having paths was not sufficient to show the second statement. Therefore, what we had to do is, instead of finding these disjoint paths, we look for these short bushes. Okay. And these bushes, they have a bunch of leaf nodes, and they're really overgrowing. And each of the leaf node is going to try to reach out, and in the sprinkling stage, they're going to connect to other bushes so that there is a higher chance of there being a long cycle. So let me use some pictures to explain what this looks like. Here, I have K bushes. They don't look like bushes, but this is kind of it's an abstract drawing. But each bush consists of L1, a set of left vertices, and R1, a set of right vertices. And we make sure that from each node in L1 to each node in R1, there exists an alternating path that starts and ends in red edges. Okay. So this is stage 1. Now in stage 2, we want to connect all these short paths together and form long cycles. This is how we do it. Let's take just a simplest example of just 2 bushes. Okay. First step, we find the set of vertices that are connected to these leaf nodes of the bushes via some blue edge.
Is bush a tree? What's a bush?
I'm going to get to that. I sort of have not explained that. Yeah, but it's basically a tree. Yeah, but it's like a 2-sided tree that because we want leaf nodes to be abundant both in the left and in the right. So it looks something like that. So we find these set of vertices that are just connected to those leaf nodes via some blue edge. Now, from the model assumption, each of those vertices are going to be incident to their unique red neighbors. Now, if by some luck, we're able to find these 2 crossing blue edges from U1 to V2 prime and from U2 to V1 prime, then I claim we're done. We have found an alternating cycle. And this is why. Because in the first stage, by construction, we have ensured the existence of some short paths, P1 and P2, that start and end in red edges. So our okay. So our path goes like this. This is not what I want. Sorry. So over here, by definition, there exists a blue edge goes like this. Then it has its unique red neighbor. Now, if we can show there is a connecting crossing blue edge here, and there's a crossing blue edge here, then you see that the alternating, the highlighted cycle here is of alternating color. So it always goes red, blue, red, blue, red, blue. And now notice that all the edges in the graph, they basically exist either from the path construction stage or just by definition. And therefore, all the edges that all we need to do is to justify the existence of these crossing edges. And in a sense, I'm sort of imagining if you step back for a moment, can basically look at this sort of complicated graph and view it as a simpler graph that just consists of 4 blobs, right? So there are some blue edges that you want to show existing among these giant blobs. And if you can show like the collapsed graph is well connected, then the cycles can be expanded into 2 cycles in the original graph. Or more precisely, we introduce this notion of supergraphs, where a supergraph node I is connected to J prime if and only if there is a blue edge that connects UI to Vj prime. So in this graph, we basically get a reduced graph that just contains 4 nodes in the supergraph, right? And now each of the alternating cycle in the supergraph expands into an alternating cycle in the original graph. And if we can show exponentially many of them, meaning that the supergraph is really well connected, then that means we have found exponentially many alternating cycles in the original graph.
This is why it's long. That's because you've taken many such subgraphs.
Yes, exactly. So now I'm just showing like a supergraph with just 4 nodes, but in reality, we want the number of nodes to scale within. Great question. So, and that's it. So, by the way, how am I on time?
15 minutes?
I'm sorry?
15 minutes?
Oh, okay. Yeah, we can do that. So, you may still have some questions remaining at this point because there are still a lot of things that I have not told you. For example, I have not told you like what these bushes look like, right? And I have not really explained why the supergraph is very supercritical. Like, why does it have such nice connect? Like, why is it that we can find exponentially many long cycles on the supergraph? And I haven't even told you where we use the assumption that D is larger than 1. Right? So next, I claim that we can answer all those questions with this one picture. So this is what a so-called bush looks like. It's a 2-sided tree. And it's constructed by this breadth first search type of mechanism, where you just take an arbitrary red edge in the middle and you grow these trees to the left and to the right. So for example, to the left, from the root node, you find the blue edges, all the blue edges it's incident to. They're going to have their unique red neighbors, and you keep doing that and end up with a set of leaf nodes. And it's pretty immediate from this picture that if you take any vertex in the left leaf nodes and then any vertex in the right, there is going to be an alternating path between them that starts and ends in red edges. Okay. So this is our construction. And also, this is the only place we used the assumption that D is larger than 1. Because note that D is the average number of vertices that each vertex is incident to via a blue edge. So in a sense, D is equal to the average number of offsprings in this branching process. And when D is larger than 1, we have with some constant probability, this branching process never dies, meaning that we can pretty much grow both sides to be as large as we want, well, without like using up all the nodes in the graph. But the reason we want the leaf nodes to be abundant is so that in the sprinkling stage, they're all of them have some probability of going out and connecting to someone else in another bush, right? And that is how we showed that the supergraph is very supercritical. So you look at all the bushes, they're all really well connected to each other. They have a very high average degree. And we can actually make that average degree as high a constant as we want. And that's how we show that there are exponentially many long cycles in the supergraph. and therefore there are exponentially many long cycles in the algebra graph. And that's how basically the whole argument comes together. So I hope that's clear. Yes, please.
In the analysis of this two-sided tree, it's not quite a branching process, right? Because after you start expanding it, the nodes that are being expanded in subsequent levels of the tree are conditioned on not reconnecting back to earlier nodes that were explored in lower numbered levels of the same tree.
Yeah, you're right.
Is that hard to address in the analysis, or is it just a minor technicality?
It's like a technicality that took some effort to address. And indeed, there's some dependence and you don't want that. Right? So the way that we handle that is basically in the construction process. After you grow after you grow a layer, then you throw away all these nodes. So you're not going to reuse them. And then in the next layer, you're going to only look at fresh nodes. And that sort of ensures independence. But this is not exactly a branching process with the same offspring distribution every time because the number of like the pole shrinks as you grow. So we basically couple it with the branching process with just a fixed number of elements in the pole to lower bound that. I hope that makes sense. So that's basically entire argument. So in the final few minutes, I would like to go back and actually get rid of this red dot here. It's really driving me crazy. Okay, there we go. So I'm going to go back and revisit the exponential graph because this is sort of a very, it's a very classical problem, I would say. Especially the unplanted version. So if you suppose like there are no fake edges and only, there are no red edges and only blue edges. So all the edges, they appear ID with the distribution equal to exponential 1. Then there is this beautiful result, which was first shown rigorously by Erdős in 2001, saying that the minimum weight matching, which is the maximum, like, not the maximum, just the minimum weight matching. It has the average weight of a beautiful constant of pi squared over 6 as the number of nodes go to infinity. So then extending their analysis, the planted version was investigated by Maharani, Moore, and Xu in 2019, and they show that under the planted model, if you again analyze the minimum weight matching, the net estimator succeeds if and only if lambda is larger than 4. So based on this analysis, they conjectured that the sharp threshold sits at lambda equals 4. So our result, as a corollary of the result, we do indeed resolve this conjecture. And I would like to point out that aside from the sharp threshold, we also show that around the sharp threshold, the average proportion of edge mistakes behaves like exponential to minus a constant over square root epsilon. So this is something that's exponentially smooth in epsilon, which is in statistical physics language, it's saying that the phase transition is of infinite order. And this was also conjectured in a previous paper by Semerjian, and and we're able to resolve that as well. Now, finally, this final remark might just really confuse you, but I have to say it. For showing this tight lower bound over here, we have to go back and resort to finding short paths instead of bushes. And the reason for that is because the bushes, if you want to control lower bound the length of the cycle, bushes are really inefficient because bushes, they contain a lot of leaf nodes, but they tend to be rather short. So if we want to find long cycles, we want long paths so that we're not wasting a lot of edges. And very luckily, we're able to do that in the exponential case. So that's basically all I'm going to talk about today. here's the conclusion. Basically, the takeaway is we established the sharp threshold. And in the exponential case, we can characterize the phase transition. It is of infinite order. And we use the sprinkling idea, which I think is really powerful. And I think it can be applied to many other problems of this sort. And finally, I'll end with some open questions that I think are interesting. First of all, can we characterize the phase transition for general distributions? So we know the phase transition for exponential model is infinite order. And we also have analysis that for the unweighted model, we show it's actually finite order. So that was really interesting for us. So we know the phase transition is going to depend heavily on the distributions, but we don't know how. And can we characterize the error not just near the transition threshold, but across the entire parameter range? And finally, would it be possible to extend our result to a planted p-factor model? Because note that a matching is basically a one-factor model. This was conjectured that the sharp threshold sits at square root k times d times the Bhattacharya coefficient b equal to 1. So I think it's possible to extend our analysis to the k-factor model as well. So it would be really cool to show that. And that's all. Thank you so much for listening.
That was astounding, but I guess time for questions. I see Christina's jumped on. Okay. In the meantime, so I have one question. So actually, I have a few. So given that you mentioned the Parisi formula for this thing.
Yeah, the pi square over 6.
Do you think there's a hope of getting a non-asymptotic version since we know the sort of Coppersmith-Sorkin formula for, since we know it for fixed time?
Yeah, so you mean like for fixing, you know, it's the sum of 1 over n squared. Yeah. Here, I don't know. Yeah, here I just don't know. I guess I guess that would be like you want to study like the finite sample behavior of this type of error. And let me think. If you follow through our analysis, you can probably find some bands, but I doubt they're going to be that tight or as pretty as the unplanted case. So I'm not sure what happens.
But one other question. The sampling result is actually incredibly beautiful because that seems like it holds for the fact that if you sample from the posterior, you're within a factor 2.
Oh yeah,
that's
right.
Specific about the planted matching.
Yeah, this is a very general observation.
So do you know if anyone else has been able to use this for other planted models? Or?
I actually don't know. Yeah, this is my first time using it, and I never. Okay. And none of my co-authors like first thought of using it as well, but it's really powerful. Yes.
In the motivation, you said that one of the reasons you're studying this problem is a particle tracking problem. Yes. I suppose the actual particle tracking problem would suggest a very different model for the random weights in the bipartite graph.
Yeah.
Something geometric.
There are
like a geometric model you would make distances. Is anything known about the recovery threshold for that problem?
Yeah, there is actually. It's I think I was seeing in 2021, a group from NYU, they derived like the sharp threshold under the geometric model, where you have like n nodes that are moving to a different location, like maybe the amount they have moved follows some Gaussian distribution, and they work out the sharp threshold for that.
Thanks.
Yeah, but you're right, that's a completely different model. Yes.
So at the last slide, when you said the open problem consists of if you looking at distributions other than exponentials, right?
Sorry, you mean
Number one.
Yeah.
Right.
Yeah.
So you can always assume that on the planted graph, the distribution is actually exponential one, just by marginal transformation, right? You can transform the weights of all. So basically, so the only question is, what do you need to assume on the sort of fake edges, right? What distribution on the fake edges, what does that mean?
Yeah, you're right. You're totally right. So far, the analysis depends heavily on the distribution of both types of edges. In particular, for the lower bound, we need to show that basically you can find these short paths with very stable edge weights.
Right, but when I say if one distribution is fixed, then you can use some like stochastic domination or something like this, right? You compare with the exponential, right? You know, I don't know, but something that's what
Yeah, you're right. I mean, yeah, without loss of general, you can always assume more of the distribution is exponential. Yeah, I'm not quite sure then what happens.
I guess the BPQ distance, I haven't really thought about it, but that must be invariant to the sort of a change of.
Oh yeah, yes, that is, because it's basically changing the dominating measure.
So yeah, so this would work.
Yeah, so the sharp threshold is the same, but the characterization of the error that could be a completely different story.
Question, do you know of comparable models where in addition to just fake edges, you might have some fake nodes or even real nodes that you can't see that get hidden somehow?
Yeah, you're right. So that's a very interesting variant model. I haven't really considered that seriously, but like you can think of these natural extensions where maybe you don't have the same number of nodes in the left and the right, and you don't have really a perfect matching, and there are some nodes that are not paired or some. So that is like an interesting extension that I have not thought about how to analyze yet.
I saw the picture of the two flocks of birds, and I started thinking, like, what if there's one extra bird on the left-hand side?
Yeah, I know. Yeah, that could totally happen. So.
Thank you.
Thank you. That's a good question.
Questions on Zoom or?
I was wondering, can you give maybe a little bit more intuition on how the proof changes when you deal with the the exponential distributions?
Yes. So I actually have some backup slides for this. So the upper bound proof is basically the same, right? You just have a first moment analysis, except now the large deviation inequality is going to just involve the Bhattacharya coefficient. The lower bound proof comes like this. Okay, so as I was saying, you need to resort to paths instead of bushes, and this is going to confuse you even more. We find these paths by using first and second moment method. Now note that these are short paths, so you're okay. You can get away with the second moment method. So you find a bunch of paths that are short, and we want their edge weights to be well behaved, in the sense that we impose some kind of uniformity constraint on the weight fluctuations on the paths. So these paths, all of them, when connected into cycles, they are going to be the so-called augmenting, meaning that they all have a higher likelihood than the truth. And we show there are exponentially number of these long cycles. By the way, so because we want like using first and second moment method, you may find a bunch of paths, but they could share edges or vertices. So in order to connect them into legitimate cycles, we need to show that there are enough number of paths that are vertex disjoint, and this is where we used Torrance theorem. So this is the overall proof idea.
Thanks.
Thank you for your questions.
No more questions. Let's thank you again.